All right, everybody, let's wrap up our discussion of goodness of fit with talking about how it is used in the context of hypothesis testing. So remember, our question that we were working with from last time is, do M&M's packages follow M&M's theory about their color's candy amount, their candy's color amounts? We take that general question, make it more specific with the research question that says, is there a significant difference between the observed M&M color proportions and M&M's expected color proportions, right? So we want to know, is what we found, is it different, significantly different from what we expected to find? Now remember, we have our same 7 steps, okay? There is the same 7 steps from the same 7 steps for every stat. It's going to look pretty much the same as the test of impedance. The only difference here is how we write our hypotheses and slightly how we would calculate our chi-square score. But from step 5 to 7 is exactly the same. Now, one thing that needs to be corrected on this slide is that we're not looking at relationships. So we're looking at differences, right? The hypotheses will say there is a difference, so there is not a difference. Goodness of fit is looking at the difference, that it hypothesizes about the difference, not the relationship, okay? So our first step is looking at our variables. We already have our variable here we talked about last time, M&M color proportions. We have the observed and the expected color proportions. And remember, our assumption is following M&M's theory about the specific distribution of the M&M color proportions. So our hypotheses, remember, chi-square hypotheses are non-directional, so we're only going to have one version of these hypotheses. The alternative is going to follow the setup of the question. Remember, if you get your research question written correctly, then the alternative will flow very easily. So the research question asks, is there a significant difference between the observed M&M's color proportions and M&M's expectation of color proportions following a specific distribution? Now, the alternative starts with saying yes to the question. There is a significant difference between the observed is said first, M&M's color proportions, that's mentioning the X variable there, and M&M's expectation, right? Saying the expectation comes second of the variable color proportions, and then the end of the sentence should specify what the assumption you're using is. Now, in our scenario, our assumption is following a specific distribution, right? M&M's theory. So the expectation that we're comparing our observed to is operating under the assumption of a specific distribution. If it was the assumption of equally distributed groups, then it would say expectation of color proportions following equally distributed groups. You would say something to that effect. So you got to add in at the very end there, after you mention the expectation of the variable, what is the assumption of the expectation that you're going with? Specific distribution or equal distribution? So essentially the alternative here is saying that the data doesn't fit the expectation, right? The data is different from the theory, right? Because if the observed is different from the expectation, it shows that what you observed, the data you got, does not fit the theory, does not fit the expectation. In fact, that's a really good way to remember the goodness of fit. The goodness of fit, chi-square, is looking at to see how good does the data fit the theory, right? A goodness of fit, how good does the data fit the theory? The alternative says the data doesn't fit. Now the null, take the same sentence from the alternative, copy paste it, and then you just change A to no. There is no, so on and so forth. And the null is essentially saying the data does fit the expectation. Since there's no difference between what you found and what you expected to find, the data fits the theory as you would have expected, right? That's what the null is stating there. So that's the second step, that's your hypotheses. So let's start to put this together. We got our scenario, 4 1-pound bags that you counted up on that one riveting Friday night. You have your research question. You have your variable and your assumption. You have your hypotheses. Of course, I shortened it here for the sake of space, but you have to write out the full hypotheses just like I showed you before. And then our third step was calculate our chi-square score, which we already did. So we got a chi-square of 15.52. Now remember, what we're looking for here is how likely were we to find this difference between O and E, right? This could have been likely for us to find, assuming the null is true, assuming there's no difference between observed and expected. But we need to determine that. Was this likely or unlikely for us to find this difference between the observed M&M color proportions and what M&M says we should have expected to find with their color proportions? So remember, what we need to do is determine is finding the difference is unlikely, and the way that using the software for the assessments, Just like you did with the test of independence one, you would use the software to calculate the specific probability, but you also need to know the workaround that we use. Remember, that workaround is using something called a critical score. So we're going to be using the chi-square critical score table to find our critical score. Remember, the critical score is the chi-square score that has a probability of exactly 0.05. So if your calculated score goes past the crit score, then it has to have a probability less than the probability of the crit score. And if the probability of the crit score is 0.05 and the calculated chi-square goes past the crit, then its probability has to be less than 0.05, because anything that goes further into the tails, the probability gets smaller and smaller and smaller. Anything past the critical score will have a probability smaller than the probability of the crit score. Anything before the crit score is going to have a probability greater than the crit score because it's getting more towards the center. So we're going to be using our chi-square critical score table again, so hope that you have that ready to look at. Now, you find the crit score using the same process as you did with the test of independence. Alpha level is your column, your degrees of freedom is your row, find the intersection. Now, calculating degrees of freedom is different for the goodness of fit. So with here, you just take the number of categories, and if your x variable minus 1. Okay, so number of categories you have minus 1. So if it was like 10 categories minus 1, your DF would be 9. Now, one important thing I want to say here, and I forgot to mention this in the test of independence section, is that when you're using the software on your assessments, it calculates the degrees of freedom for you. So when you look at the tables after you use the software, the output, you just have to look for the box that's labeled DF, and it will show you the number there for you. That's the degrees of freedom. You need to know how degrees of freedom are calculated because you need to know that concept. You may be asked a question like on the quiz about the degrees of freedom, but you won't have to do it by hand on the assessments, okay? The software will calculate them for you. So how would we find our critical score? Go ahead and look at your table. And our DF is 6 minus 1. We got 6 M&M colors. Minus 1 is 5 colors total. So you take 5 as your DF, 0.05 as your column, and find the crit score. Now, the crit score you should have found is 11.07, okay? And now we compare our calculated score to the critical score. And as you can see, our calculated score goes past our critical score, okay? Which means that it has to have a probability less than the probability of the crit score. The crit score's probability is 0.05, then our calculated score's probability has to be less than 0.05. So it goes past, probability is less than, meaning it is statistically significant, meaning that this chi-square score was unlikely to find, assuming that there is no difference between the observed and expected color proportions. So because our chi-square score is statistically significant, we're going to reject the null, and we're going to go with our alternative, and that is your conclusion. So that's your research conclusion. You restate whatever hypothesis you chose to go with. So we're going to restate our alternative. There is a significant difference between the observed M&M's color proportions and M&M's expectation of color proportions following a specific distribution. Very technical conclusion, right? So what's the final thing we have to do? We have to find our general conclusion, phrase our general conclusion, which is a more simplistic version of the research conclusion. Put it back in the language of the general question, make it a little easier to understand. So a way that we could write that is M&M's actual color amounts don't match M&M's theory. Because essentially that's what the alternative says. The alternative says the data doesn't fit the theory. So we say that, well, M&M's actual color amounts don't match M&M's theory. And that is how you do the goodness of fit chi-square in the process of hypothesis testing.